All right, welcome. Have you ever really stopped to think about what it takes to turn a pile of coal into the electricity that's powering, well, everything around us? It's a truly massive challenge, right? How do you take that raw chemical energy and turn it into this huge grid-scale electrical power? Well, today we're going to break down exactly how modern steam generators pull it off, and we're going to look at it as a series of really brilliant solutions to some incredibly tough problems.
Okay, so let's take a look at this. I know. This master diagram looks pretty complex at first glance. But honestly, the best way to think about it is like a roadmap of solutions. We're going to walk through this whole system piece by piece and really uncover the four big engineering problems it was designed to solve.
So, before we get into all the nitty-gritty details, let's just be super clear on the fundamental goal here. The mission statement is simple to say, but wow, is it hard to actually do? You have to take all that chemical energy that's locked inside the fuel and somehow convert it into stable, reliable electrical power. And every single component we're about to look at is an absolutely critical link in that chain.
All right, let's kick things off with our first huge engineering hurdle, the pressure problem. Look, to generate any kind of serious power, you need to create steam with enough raw force to spin turbines that are like the size of a small house. This is definitely not your stovetop kettle we're talking about here. This is about creating just immense, perfectly controlled pressure. So that brings up the core question, right? When you boil water at home, what do you get? You get bubbles. But on an industrial scale, those bubbles are a huge problem. They represent instability, they represent wasted energy. So the real challenge is, how do you get around that? How do you create this perfectly uniform, incredibly powerful jet of steam? Well, the answer, it turns out, is to just push the water way past its normal limits. You take it to these incredibly high, they're even called supercritical pressures. And when you do that, you can actually force it to change state from a liquid to a gas instantaneously. And the key part? No bubbling at all. And this is where the hero of our story comes in. The Benson boiler. This piece of gear is an absolute marvel, designed specifically to handle these insane pressures. Because it operates beyond that critical point of water, it doesn't need a big, clunky drum to separate steam from water. Nope. The water just flashes directly into this super pressurized, perfectly uniform steam. So why go through all this trouble? Well, the payoff is huge. By getting rid of that heavy drum and operating at these crazy pressures, the Benson boiler achieves some incredible results. We're talking up to 90% thermal efficiency. It's 20% lighter than other boilers, the explosion risk is basically zero, and you can get it up and running in just 15 minutes. It is a total game changer. Okay, so problem one, pressure, solved. But that initial combustion happening in the furnace, it generates a just staggering amount of heat. So that brings us to our next big challenge, making sure that not a single bit of that precious energy goes to waste. Think about it for a second. Once the main job is done, turning water into steam, you're still left with these incredibly hot exhaust gases. If you just let all that gas escape up a chimney, you're basically just throwing away a massive amount of free energy. It's like leaving money on the table. So how do you capture it? The solution is actually a series of really clever heat exchangers. Let's go back to our big diagram for a sec. See, after the boiler, those hot exhaust gases are sent on a journey. They're routed through three key players, the superheater, the economizer, and the air preheater, long before they ever get a chance to escape. So first up in the lineup is the superheater. Its job is to take the steam that just came from the boiler and, you guessed it, heat it up even more. This creates what's called dry superheated steam, and that's awesome for two reasons. One, it carries way more energy, so you get more power. And two, and this is super important, it gets rid of any tiny water droplets that could literally shred the turbine blades over time. Now this is where the whole design gets really clever. Next, the exhaust hits the economizer, which uses that heat to pre-warm the water before it even gets to the boiler. Then the air preheater uses the very last bit of leftover heat to warm up the air that's going to be used for the combustion itself. The system is literally recycling its own waste heat to make itself more efficient right from the start. It's this brilliant, self-reinforcing loop of efficiency. All right, so we've got pressure handled, and we're squeezing every last drop of energy out of the heat. But what about the stuff left over? Burning fuel, especially coal, creates a major byproduct, ash. And this isn't just a minor cleanup job. It's a huge logistical challenge. Just try to picture it. When you're burning tons of coal every single hour, you're not left with a little pile of ash in a fireplace. You've got a constant, continuous stream of this hot, gritty, abrasive material that you have to get out of the furnace. And you have to do it safely and cleanly without making an absolute mess everywhere. Well, one of the coolest and most effective solutions is something called a pneumatic ash handling system. Forget about messy conveyor belts or sloshing water around. This system basically works like a giant, superpowered vacuum cleaner. It uses air to suck all that ash through a completely enclosed network of pipes and shoots it directly into a storage silo. And this, right here, is a perfect example of a core concept in all of engineering. There are always trade-offs. On the one hand, the pneumatic system is fantastic. It's totally dustless, no spills, super clean. But that comes at a cost. Blasting all that abrasive ash through pipes at high speed causes a ton of wear and tear, which means higher maintenance bills. Oh, and yeah, they can be pretty noisy too. Okay, so we figured out how to handle the solid waste. That brings us to our final big challenge. And it's another kind of waste heat. So after that steam has done its job and blasted through the turbine, it gets condensed back into water, so it can be used again. But now, that water is incredibly hot, and that creates a whole new problem we've got to solve. You obviously can't just pump boiling hot water right back to the beginning of the cycle. It just wouldn't work. You have to cool it down, and you have to do it efficiently. And remember, for a big power plant, we're not talking about a small amount. We're talking about cooling millions of gallons of water continuously 24/7. And one of the most elegant solutions is also one of the simplest, the spray pond. Instead of building some crazy, complex refrigeration system, this method harnesses one of the most powerful cooling forces on the planet: simple evaporation. So here's the magic behind it. The hot water gets pumped through a whole network of nozzles that spray it high up into the air, creating a fine mist. Why do that? Well, it dramatically increases the surface area of the water that's exposed to the air. And as a little bit of that water evaporates, it carries away a huge amount of heat with it. This rapidly cools down the rest of the water, which then falls back into the pond, all ready to be used again. Simple, but so effective. So let's bring it all back home and look at our big diagram one last time. It all makes sense now, right? We tackled the pressure problem using the Benson boiler. We solved the efficiency problem with that clever team of a superheater and preheaters. We figured out how to manage waste with the pneumatic system, and we handled all that excess heat with cooling ponds. You see, each part isn't just a component. It's a specific solution to a specific problem. And together, they form this one powerful, incredibly cohesive system. You know, it's really a testament to decades and decades of innovation. Every single one of these components represents an elegant, clever solution to a very real, very difficult engineering problem. And the amazing part is that they all have to work together, perfectly, seamlessly, just to keep our lights on. And, you know, that really brings us to our final thought for today. These systems are, without a doubt, incredible feats of engineering. But the quest for improvement, it never ever ends. The next generation of engineers, maybe some of you watching, are going to face the challenge of taking these systems and making them even more efficient, even cleaner, and way more sustainable. So the real question is, how are we going to do it?